In this segment, we'll talk about speed and velocity. Okay, speed is known by most of us. The definition of speed is distance over time. Think about it in terms of speed limits, like in the highway. What's the speed limit? 55 miles per hour, that's 55 miles over 1 hour. Distance over time. Now, the units for speed are meters per second, that's the international system of units, or miles per hour, or kilometers per hour, or whatever. Now, when we discuss speed, direction is not important, like distance. It does not depend on direction. However, speed is always positive. An object is either moving or not moving. There is no negative speed. So that's key. Speed is always positive. For example, what is the average speed of a racehorse that runs 1,500 meters in 2 minutes? Okay, so the distance traveled is 1,500 meters. The time is 2 minutes. So the speed is distance over time. In this case, 1,500 meters over 2 minutes. So it's going to be 750, I lost the 5, 750 meters per minute. Since they didn't tell me to express the answer in particular units, I can leave the answer here as meters per minute. But just the sake of review, I'm going to change the unit to meters per second. So if I have a speed, that's equals 750 meters per minute. To convert it to meters per second, to get rid of the minutes, I need to put 1 minute here on the numerator to cancel the minutes. And a minute, I'm going to write what is it equal to in seconds here. 1 minute is 60 seconds. So the minute cancel out, and I end up having 750 over 60 meters per second, or 75 over 6 meters per second. Now, velocity is different. Velocity is the vector here. We define it as change in position, which, remember, is a displacement. Over the time it takes the change to occur. The unit is again meters per second, miles per hour, or whatever, but here the direction is important. It is a vector. A velocity is both a speed that we measure in meters per second and a direction. Now look at the way we wrote it in terms of a formula here. The symbol here, the bracket here, is try to say the average velocity between TF and TI. TF is a final time, TI is the initial time. Now PI is the position at TI. PF is the position at TF. Now PF minus PI is what we call the displacement. TF minus TI is the time for that displacement. Okay? So that's our equation. Average velocity for a time interval t is going to be the displacement during that time over the time t. And remember, displacement is a change in position. Now, a slight reminder here. Remember Newton's first law? When it says a moving object will continue moving in a straight line at a constant speed. Straight line at a constant speed. What that was talking about is moving at a constant velocity. A constant velocity would be a velocity that does not change direction and that does not change in magnitude, in the amount. So Newton's first law, when we use velocity, is going to be expressed. A moving object will continue moving at the same velocity, and a stationary object will remain at rest unless acted upon by an unbalanced force. Now, how do we get a constant velocity? Oh, sorry. How do we get a constant velocity? The two things, like what we had in the previous screen, that are important to keep unchanged, you cannot change either one of them. You cannot change the direction, and you cannot change the magnitude. Remember, the magnitude of a velocity is a speed. Oh, oops. Now, one remark here about Newton's first law of motion. It says an object moving at a constant velocity will keep on moving at that same constant velocity. An object at rest will keep moving at rest unless acted upon by an unbalanced force. So there we have a definition that I'm going to introduce. An object, for example, or a system, think of yourself in a van. If your van is at rest, the physics in your van is going to be the same as the physics just outside the van. For example, if you drop an object, it's going to behave the same way inside the van as outside the van. The object at rest, in this case the van, we say it is in static equilibrium. It is in equilibrium. It is at rest, static, and there are no unbalanced forces acting on it. Now, if you are again in the same van, but the van was moving at a constant velocity, was not speeding up or slowing down. Again there, if you toss something, it's going to behave the same way as if the van was at rest. However, if the minute you toss something up, the driver of the van decides to speed up, whatever you toss is not going to fall back in your hand. If he's going to speed up, it's going to fall behind your hand. If instead the person decides to brake, whatever you toss is going to fall in front of your hand. Now, in either case, if the van is speeding up or slowing down, the van is not in equilibrium. When it is moving at a constant velocity, we say that it is in equilibrium.